Here's an example problem of showing that these two subspaces represent the entire space as a direct sum. So you have to prove two things. One is that you can take any element in here and represent them as a sum of one element from here and another element from here. That's one. The other is you have to show that it is a direct sum. The previous one only shows that P3x is u plus v, and then you have to show it's a direct sum. Of course, you can show it by saying that anything in here can be uniquely represented as sum of something plus sum of something, but we're also going to make use of a theorem that we proved in the previous one, which is that if you just have two subspaces, showing that their intersection is 0 is enough to prove that the entire space is a direct sum. Okay? Well, I'll explain that further once we get there. Okay? So first, proof. In order to show that any f of x in P3x satisfies f of x equals to some function g of x plus h of x with g of x in u and h of x in v. So that's what you want to show. So this will be our claim that we want to show. That shows that P3 will be equals to u plus v. Not yet a direct sum, we just show that it's u plus v. But in order to show this statement, as we have learned last time, anytime you want to show a statement like this, you first have to investigate each one of these parts and try to think what it means. So f of x is in P3x. What does that mean? Well, P3x is the vector space of polynomials of degree 3 or less with real coefficients. So why does this satisfy the vector space? Well, to show that you would need to show all the 8 properties of being a vector space, so it's going to take some time. But this question says it is a vector space, so we're going to accept that it is a vector space. It's given. And elements in P3 of x are polynomials of degree 3 or less, so it's ax cubed plus bx squared cx plus d with a, b, c, d in real numbers, right? So instead of this, you replace this statement by this other statement, okay? Let's do the same thing for the other ones. What does it mean to be in U? Well, so gx is in U, but U is a subspace of P3x. So a priori, g of x also looks like something x cubed, something x squared plus something like this. And now I'm kind of regretting the choice of A, B, C, D because I used too many letters already. So let me be conservative. I'll put something like A1, x cubed a2x squared plus a3x plus a4. Okay? And then with g of 0 equals to 0, but since, what is g of 0 according to here? If you plug in x equals to 0, what do you get? A4, right? We have A4 equal to 0. Okay? In other words, we have just shown that being in here implies that g of x looks like a1 x cubed plus a2 x squared plus a3 x. Sorry about writing over the previous one, but hopefully that makes sense, right? In other words, the constant term has to be 0. Okay? And in fact, we do see that if it looks like this, if you plug in 0, you get a 0, right? So that's good. And then what about h of x? Well, h of x belonging to v just means that h of x, the condition is that it has to be some constant, right? Now, unfortunately, we already used c here, so we'll just put c1. So this investigates what it means for each of these elements to belong in these sets, right? Okay, so now let's try to rephrase the question with this newly developed insight and see if it makes sense, okay? So what are we trying to prove? We're trying to prove that this guy here is a sum of polynomials that look like this one and a constant. Oh wow, that just seems obvious, right? How do you make this equal to something that looks like this plus something that looks like this? To do that, A1 must be, for this to be this plus this, A1 must be A, and A2 must be B, A3 must be C, C1 must be D. That's all, right? Okay, so what we are going to say is we can say that if f of x is in P3 of x, then f of x equals to ax cubed plus bx squared plus cx plus d, which is equal to ax cubed plus bx squared plus cx parenthesis plus d, and ax cubed plus bx squared plus cx is in U because if you plug in 0, this is equal to 0. Okay? These are polynomials. If you plug in 0, you get 0. That's the description of U. So we've shown that this part is mu. Still and D is in V by definition. It's like it's only taking constant functions, so it's just the constant, so that's that. Therefore, P3 of x is equal to U plus V. In other words, anything that you can find in P3 of x, you can represent them as a sum of an element in U and a sum of element in V. Now, when you write down the final answer, everything that we wrote here actually need not be there. You don't need to write all this. You just want to start from here. Okay? You say, if you pick any element from P3 of x, then you can split them as that, and it has to be, we see that the first part belongs to U, and second part belongs to V. Therefore, we've shown that P3 of x is U plus V. That's it. Yeah. We didn't have to write all the things that I wrote here, but I'm trying to really make it clear that often it's not just the things that you read that's what's going on in the minds of the person who is writing this proof. Okay? You have to be able to think much wiser than the proof that you read. You have to read behind the lines, behind the scenes, or else you can't have a good understanding of how proofs work. Okay? All right. Okay, so that part is done, but now you have to show that it's a direct sum. To show direct sum, we had this theorem. So let me just write here and erase, hopefully you remember. So theorem is that if, say, V is U1 plus U2, and U1 and U2 had intersection as only the zero element, then we know that V is equal to U1 direct sum U2. That was something that we proved last time, at the end of last time. So we want to make use of this because we just have two subspaces. Now, for some reason, if you have three subspaces, then you don't have such a theorem, okay? You can think about what kind of theorem you might want to write for three things, U1 plus U2 plus U3. Maybe you think U1 plus U plus U2 plus U3 with U1 intersect U2, U2 intersect U3. Maybe that's right. So if you do U1 intersect U2 intersect U3 to be 0, that's not enough. But maybe pairwise intersection be 0. Yeah, maybe that's enough. Okay. All right. So because we're going to use that, furthermore, if some, well, I already used f of x, let's say g of x. If g of x is in U intersect V, then g of x in V implies that g of x is what does that imply? if g of x is in V, what do we know? Yeah? Just read what V is. What does that say? It's a constant, right? Now, we already used all the letters A, B, C, D, so I don't want to use E because that's like the E 2.7 something. Let me use K for some K in R. I have to take this call. It's my dad. 여보세요? 예. 예, 지금 수업 중인데. 예. 예, 무슨 일이에요, 근데? 아. So I should probably do not disturb. I always keep forgetting. Let me see, do not disturb. Okay, done. Okay, so gx in V implies that g of x equals to k for some k equals r. Okay, good. But then, I'll say and g of x in U implies that, what's g of 0 now? If g of x is k, what's g of 0?
0.
Well, not yet. If I plug in x equal to 0, you just get k.
Oh.
Right? So you say k, but then being in U implies that g of 0 is 0. Right? So that means k is 0, but since g of x is k, that means g of x is 0. Now let's see what this much proves. I picked any arbitrary element in U intersection V, right? What did I find out? I found out that g of x ends up being 0. What kind of set has a property that you pick anything, it's always 0? It's the set with only the 0, right? Okay. So this shows U intersect V is 0, and therefore, what's the number of the theorem in the linear algebra done right? 1.4445? 1.45, right? So, and by 1.45 of our textbook, we ended up showing that it's a direct sum. Okay. So starting from here and the end, that's the perfect solution for this question. And I kind of explained how I came up with this part. Okay. You come up with this idea only by investigating what you're trying to prove and think about what each part means. This kind of comes up naturally. Now this one, I wrote down the proof, but I really didn't explain what my thinking process was. Okay. My thinking process was, well, I need to show this. That's where I start, really. Okay. So a lot of times the proof that's written down is the opposite order of the actual thinking process that went before writing the proof. My real thinking process is, well, usually if you have two sets and you want to show direct sum, this 1.45 does it. It's the easiest way to do it. Okay. Now, therefore, I need to show this. How am I going to show this? Well, what kind of property does a set with only 0 element have? It has the property that no matter what you pick from it, you end up being forced to have 0, right? And now you investigate what it means to be in here and here. That means, being in the intersection means it has to be in both of them. This one says the constant term shouldn't be there. This one says you should only have the constant term. So how am I going to use both of them to show that the only way to be in the intersection has to be 0? Well, I could have started with this one, but that makes this element look much more complicated. It's better to start with gx being in V, because that narrows down what gx can be considerably, right? Yeah, it's a lot easier to argue with this V first. So even though I wrote U intersection V, you want to start with this and say, oh, gx is just a constant. Now, given this, let's see what it means to be in U, and then you realize, well, for this property to work, that constant that I chose must be 0. If that's 0, this has to be 0, and now therefore this is true, and therefore it's a direct sum, and you're done. Okay? So you should be able to read a proof and think about what went before the proof. Okay? All right, so hopefully that was helpful.